Welcome to the course Chemical Engineering Process Calculation. Today's topic is material balances. Broadly speaking, in chemical engineering, the processes are divided into three categories: batch, continuous, and semi-batch. I would suggest you pause the video for some time and read the definition. If you have gone through the definition, like if the system variables, one point to note, the steady state, when we call a process to be steady state or transient or unsteady state. If the process variables like temperature, pressure, volumes and flow rates, if it changes with time, we would say it is transient or unsteady state. If it is independent of time, then steady state. So the batch and semi-batch would be unsteady state. When to use batch process? When we want small quantities of product. This is the most general equation you'd see in chemical engineering. It could be applied to mass, species, either energy and momentum. The balance is as follows: input plus generation minus output minus consumption equals to two types of balances you should know: the differential balances and integral balances. Differential balances is where each term is rate, like rate of input, rate of generation. That would be like people per year, gram SO2 per second, whatever gram eggs per second. This is generally applied to continuous process. Each term would be amount, like gram, lbs, kg, and this would be mostly applied for batch process. So integral for batch process, differential for continuous process. Yeah, one more point to note. If you're using this balance equation for mass, the generation, consumption and accumulation term would be zero. As we know, mass cannot be generated, nor can be consumed, nor it gets accumulated, except for nuclear reaction that will vary. But in general cases, for mass it will be input equals to output, as you can see. And if the balanced substance is non-reactive, so the balance, this general balance would be reduced, and the generation term would be zero and the consumption term would be zero. And for steady state, this accumulation term. Now let's look at the example. 1000 kilograms per hour of mixture of benzene and toluene containing 50% benzene by mass is to be separated by distillation into two fractions. The mass flow rate is mentioned of top stream and toluene in the bottom stream. The operation, point to note, the operation is at steady state. This is one of the solved example in the book. I'd be solving this first question. I would suggest please pause the video and read the question. As we know, this is a general balance: input plus generation minus output minus consumption equals to accumulation. This is the general balance. For steady state, accumulation term is zero, and other cases we have considered, like mass, it will be input equals to output. If there is no reaction, there will be generation, and consumption term would be zero. This is the feed as mentioned in the problem, and this is the top product and this is the bottom product. This is a distillation column. And we'll be applying first total mass balance. This should be the equation. Input equals to output. As you can see, this would reduce to this equation. This is the first equation, and we'll again apply balance over any of the substance. Like I have applied the balance for benzene total mass balance for benzene, like input equals to output, as simple as that. In solving, we would get m2 is equals to 50 kg per hour, and using this equation we'll get m1 is equals to 25 kg per hour. We could verify this by doing our toluene balance, that it comes out to be same 25 kg per hour, that our process is fine. Let's look at the next example. Please read the question. I will suggest you pause the video for some time and go through the question. Okay. This is the second example. As per the question mentioned, this is the feed 200. This is one feed. This is the other stream. These two are feeds. It's given as this is 0.4 is the is the mass fraction. Mass fraction of methanol, and 0.6 is mass fraction of water in 200 gram solution feed, and this is 150 gram, and this is as follows. So we need to calculate m and x. X is mass fraction of methanol, so 1 minus x would be the mass fraction of water, as we know summation xi equals to 1, that is xi is a mass fraction of ith particle. There are only two particles, so okay. Applying the total mass balance, you could see we get m is equals to 350, as simple as that. Next we'll apply the mass balance for methanol, and it will reduce, as we have already found the m we're gonna use, and we get the mass fraction, that is 53% is MEOH, methanol in product. Okay, we go to the next question. I would again suggest please pause the video and read the question carefully. Yeah, as we did balance on continuous process, that was example 1, and then the balance on batch process, that was example 2, and now we go for semi-batch process. Yeah, as per the diagram, this is the tank. It contains liquid hexane, and air is passed, and it gets some amount of liquid comes out with the air. This is the input stream, this is the output stream. Now the question asks, what would be the time to vaporize the quantity of liquid, that is 10 meter cube. As we know, this is the general balance equation. Input plus generation minus output minus consumption equals to output equals to accumulation. So we'll be applying it for air. As we have seen the general balance equation, for air it would be input equals to output. So the input is 0.1 kilomole air per minute, that is equals to 0.9 into n dot 0.9 is a mole fraction, and here in solving n dot comes out to be 0.111 kilomole per minute. If we apply next the balance for hexane, it would be accumulation equals to minus output. We could see there is output of hexane in the product stream, output, that is hexane, and there would be accumulation. Obviously there is a change, there is no input. This would be the balance for hexane. It would be a semi-batch process. From, let's say we consider from time t is equals to 0 to time t naught. The change in moles, we need to find that. it would be like we don't know the specific gravity. Okay, for the question, the specific gravity we can consider it to be for liquid hexane it will be 0.659, and the liquid volume that gets evaporated is 10 cm cube. So the change in moles would be in solving liter, that is in kg per liters. So we need to convert this this 10 meter cube in terms of liters. This will be the conversion, and this is the molar mass of hexane, and in solving we get delta n to be this comes around minus 76.45 kilomole of hexane. So now it's simple. We just apply that. Accumulation term is minus 76.45 equals to minus 0.1 and dot, that is in mole fraction, that is in molar flow rate. Mass, this is the mole fraction, this is the mole flow rate, and we want time, so multiply with t, and t naught as per the variable assumed. So t naught comes out to be 6880 minutes.